Hi, everyone. Welcome back to Introduction to Artificial Intelligence and Machine Learning. In the previous session, we give an overview and introduction on classification models, various classification algorithms, and how to evaluate classification models. In this session, we will focus on supervised learning and regression algorithms. The first question I'm going to ask, what is regression algorithm? Regression model is a statistical method to model the relationship between an output, which is a target, and an input variables. So regression algorithm is a subset of supervised learning. Regression analysis helps us to understand how the value of the output variable is changing corresponding to an input variable. So regression is going to predict continuous or real values such as temperature, age, salary, and price. Let's take a look at one concrete example of regression analysis. Suppose there is a marketing company called A, who does various advertisements every year and gets sales on that. The below table shows the advertisement made by the company in the last 5 years and the corresponding sales revenue. Now, the company wants to do the advertisement of $200 in year 2022 and wants to know what the prediction about the sales for that year. So, in order to solve such type of prediction problems in machine learning, we need to build a regression model. The model can figure out the relationship between advertisement costs and the sales revenue. When there is a new input coming, here it is the advertisement cost in 2022, the model can predict the sales revenue accordingly. As mentioned above, regression model helps in the prediction of a continuous variable. There are various scenarios in the real world where we need some future predictions such as weather forecast, sales prediction, marketing trends, etc. So for such case, we need regression, which is a statistical method and using machine learning and data science. Regression estimates the relationship between the target and the input variable, find the trend in data, and predict the outputs. Moreover, by performing the regression, we can confidently determine the most important factor, the least important factor, and how each factor is affecting each other. Same for classification algorithms. There are various types of regression algorithms which are used in data science and machine learning. Each type has its own importance on different scenarios. But at the core, all the regression models analyze the effect of the input variable on output variables. Here, we are discussing some important types of regression, which are given below. We have linear regression, polynomial regression, support vector machine, decision tree regression, random forest regression, and lasso ridge regression. In the following section, we are going to deep dive into each of the regression algorithms. Firstly, let's talk about linear regression model. Linear regression fits a straight line to the data sets. This is one of the very simple and easy algorithm which works on regression and shows the relationship between the continuous variables. But it is surprisingly applicable to a wide range of problems. If there is only one input variable x, then such linear regression is called simple linear regression. And if there is more than one input variable, then such linear regression is called multiple linear regression. The relationship between variables in a simple linear regression model can be explained using this image. Here, we are predicting the frozen yogurt sold on the basis of temperature. And we can clearly see that the higher the temperature, the more yogurt sold, and which makes sense. The mathematical equation for linear regression is simply y equals a multiply x plus b, while a and b are the linear coefficients. To be noted that almost any curve can be divided into different pieces of linear models. The second regression model I'm going to talk about is called Polynomial Regression Model. Polynomial regression is a type of regression which models the nonlinear dataset using a linear model. It is similar to multiple linear regression, but it fits a nonlinear curve between the value of x and corresponding conditional values of y. Suppose there is a dataset which consists of data points which are present in a nonlinear fashion. So, for such case, linear regression will not best fit to those data points. In order to cover such data points, we need polynomial regression. In polynomial regression, the original features are transformed into polynomial features of given degree and then modeled using a linear model, which means the data points are best fitted using a polynomial line. The model is still linear, as the coefficients are still linear with quadratic. Let's say if there is a 2-degree polynomial, then the feature x will become x squared, and so on. The next model I'm going to talk about is decision tree. I think some of you can still recall decision tree can be used in classification model as well. So here, decision tree is actually a supervised learning algorithm which can be used for solving both classification and regression problems. You can solve problems for both categorical and numerical data. It breaks down a dataset into smaller and smaller subsets, while at the same time, an associated decision tree is incrementally developed. The final result is a tree with decision nodes and leaf nodes. If you look at this diagram, we use different decision tree to model the relationship between the data and target. You may notice one potential problem. And yes, the issue for decision tree regression is that it can be easily biased by outliers or those very extreme values. And we call this phenomenon overfits. In order to solve this problem, we prefer to use random forest, which is an ensemble learning algorithms that combines many different decision trees and predict the final output based on the average of each tree output. Here comes support vector machine again. Support vector machine is similar to decision tree. It is a supervised learning algorithm which can be used for both classification and regression models. When we use it for regression problems, then it is termed as support vector regression. Consider these two dashed lines as the decision boundaries and the blue line as the hyperplane. In support vector regression, we always try to determine a hyperplane with a maximum margin so that the maximum number of data points are covered in that margin. The main goal of support vector regression is to consider the maximum data point within the boundary lines, and that the hyperplane, which is the best fit lines, must contain a maximum numbers of data points. Finally, we are going to talk about rich and lasso regression models. Rich and lasso regression uses regularization technique to reduce the complexities of the model by introducing a small amount of bias. The amount of bias added to the model is known as regression penalty. We can compute this penalty term by multiplying with the lambda to the weight of each individual features. These regularization techniques can be used to improve many models, including simple linear regression models or even complex neural networks. It can improve both model accuracy and generalization. Generalization is how well the model works on unseen data points, and this is about longer-term model performance. It is hard to say whether rich or lasso regression is better. For rich regression, we are using the square of the weight to penalize the model complexities, while for lasso, we are just using the absolute value of weight to penalize the model. In short, lasso regression tends to do well if there are a small number of significant parameters and the others are close to zero. While for rich regression, it works well if there are many large parameters of about the same value. Evaluating a regression model is as important as building it. We are creating models to perform on new, previously unseen data. Hence, a thorough and versatile evaluation is required to create a robust model. So here, we are using different evaluation metrics in order to see how good our regression model performs. We have mean absolute error, mean square error, root mean square error, mean absolute percentage errors, and R-square. And in the following section, I'm going to give you more details about each of the evaluation metrics and what's their advantage and disadvantage. Firstly, let's talk about mean absolute error, MAE. Mean absolute error is a very simple metric which calculates the absolute difference between actual and predicted values. To better understand, let's take an example. You have input data and output data and use linear regression, which draws a best fit line. Now, we have to find the mean absolute error of your model, which is basically a mistake made by the model known as an error. The difference between the actual value and predicted value is an absolute error. We will sum up all the errors and divide them by a total numbers of observations. And this is called mean absolute error. And you can refer MAE to the equation here. Our aim is to minimize mean absolute error because this is a loss term. Similarly, we have another evaluation metric called mean square errors. Mean square error is a most used and very simple metric with a little bit of change in mean absolute error. Mean square error states that finding the square difference between actual and predicted values. So, above we are finding the absolute difference, and here we are finding the square difference. What actually the MSE represents? It represents the square distance between actual and predicted values. We perform square to avoid the cancellation of negative terms, and this is the benefit of MSE. Another benefit of using MSE is that MSE is differentiable, so you can easily use it as a loss function. However, the value we got after calculating mean square error is a square unit of output. And if we have outliers in the datasets, it penalizes the outliers a lot, and the calculated MSE can be very large. In short, it is not very robust to outliers as compared to mean absolute error. As root mean square error is clear by the name itself, that it is a simple square root of mean square error. The advantage of RMSE is that the value we get is in the same unit as the required output variable, which makes interpretation of this loss term easier. However, it is not that robust to outliers as well as compared to mean absolute error. Most of the time, people use root mean square errors as an evaluation metric, and when we are working with deep learning techniques, the most preferred metric is RMSE. Finally, we have mean absolute percentage errors. This is one of the most commonly used KPIs to measure forecast accuracy. Mean absolute percentage error is the sum of the individual absolute errors divided by the actual value. It is the average of the percentage errors. The advantage of MAPE is that it is expressed as a percentage, which is scale independent and can be used for comparing forecasts on different scales. Therefore, it is easy to explain to stakeholders. Please take note, the values of mean absolute percentage error may exceed 100%. That is, when your actual value is small and the predicted value is very large, the percentage error can shoot really high. As a consequence, mean absolute percentage error will favor models that under-forecast rather than over-forecast. And the last metric we are going to talk about is R-square. R-square score is a metric that tells the performance of the model, not the loss in an absolute sense that how well did the model perform. In contrast, mean absolute error and mean square errors depends on the context, as we have seen, whereas the R-square score is independent of context. Hence, R-square is also known as coefficient of determination, or sometimes also known as goodness of fit. When R-square score equals to 0, that means we are using the average to make predictions. When R-square score is 1, that means the regression line doesn't make any mistake. It is perfect. In the real world, this is not possible. So we can conclude that as our regression line moves towards perfection, R-square score moves towards 1, and the model performance improves. The normal case is when the R-square score is between 0 and 1, such as 0.8. And that means your model is capable of explaining 80% of the variance of data. After introducing various evaluation metrics, you may probably wonder which is the best evaluation metric for regression models. We have to say there is no silver bullet. We should always choose the most suitable metric based on the actual situation. And this is the end of supervised learning regression model. In this session, we introduce the definition of regression, various regression algorithms, and different ways how to evaluate a regression model.